you're going to see Earth get smaller and smaller and smaller and smaller. And that delay is going to get bigger and bigger and bigger and bigger. And then you become more Martian.
And that was Dr. Emma Chapman, a Royal Society Research Fellow, lecturer in astrophysics at the University of Nottingham, and author of The Echoing Universe, to talk about radio astronomy, the invisible light all around us, and the strange intimacy of studying the universe through signals we cannot see. Together, we explore how radio astronomy helps us understand the moon, Mars, the early universe, alien communication, AI, space weather, and the future of telescopes on the far side of the moon. Along the way, we talk about the astronauts' wives waiting for signals from Apollo, the emotional force of seeing a comet as a child, why mathematics may be the only language we share with extraterrestrial life, and how telescopes turn invisible waves into a new kind of cosmic vision. And how telescopes turn invisible waves into a new kind of cosmic vision. I'm Autumn Fidef, and I'm joined by my co-host Noah John Syracusa on this episode of Breaking Math.
So, Emma, to start out, can you tell us about the fruit bowl of astronomy? I thought this is this wonderful metaphor that you start your book with, and I'd love for you to share it with us.
Sure. So this is the idea that if you imagine you're in your kitchen or wherever you keep your fruit bowl at the dining table, and you've got a whole selection of your favorites in there, bananas, apples. These are the really easy fruit to eat, right? You just grab an apple. I just had one. You grab an apple, you eat it. You peel a banana, you eat it. This is, for me, how I think of the more quotation normal part of the electromagnetic spectrum, or light, like optical light, like our eyes can see. So like apples, you could really easily eat them. Optical light, you just have to open your eyes and look. Whereas radio astronomy, that's the fruit that requires a bit more prep. So I write in the book that it's like the lemon. It's the lemon of the fruit bowl. And it's the lemon because, yeah, you know what? You can't just take a bite out of it. You need a bit more intuition, I suppose. But once you've prepped it, and this is where I just got hungry, basically. I was literally looking at a lemon. I'm like, oh my God, I want some lemon drizzle cake. And I was like, oh, that's kind of like radio light. Because when you take the time to cut it and bake it and combine it, it turns into this amazing concoction that you can eat and learn so much more about the universe when it's radio light. So yeah, that's the idea of it. A bit of a muddled thing in my mind when I just got hungry, I think.
But
So,
I love how it captures this fact that there's the most accessible thing that comes to mind first, and there's the thing that we have to work a little bit more, but can be really wonderful and enriching. And I thought that's a great way to think of the different light spectrums.
yeah, I mean, who doesn't prefer a slice of lemon drizzle cake to an apple? Let's be honest here. So, like, you know,
Well,
you
let's
take
not get too controversial.
yeah, I'm sorry, I've just lost half the audience. But Apple people, you're welcome to. It's radio light. It's one of the reasons I wrote the book was because if you tell people that you're an astronomer at a party, like there's a good section of society that will get really excited, and they'll either ask you about their star sign or black holes, and that's fine. And then there's another part that you'll say, oh, I'm actually a radio astronomer, and they'll just walk away, like politely see somebody over your shoulder and drift off into the party. And I think it's just that radio astronomy, it just comes across as really daunting because we don't understand what it is. And once we tell people, it's just, you just got to take one more step, and then there's an incredible universe to look at.
So tell us a little bit about what radio astronomy is and the difference between optical astronomy, because optical astronomy has such a strong visual hold, especially on the public's imagination.
So radio astronomy, it combines two really familiar concepts. So that's the radio, which if you're old enough to remember, you might have had a radio with a pull-out antenna and actually tuned it to stations to listen. And then there's astronomy, which is looking up and the study of the universe. And radio astronomy is combining those two concepts together. So it's using radio waves to study the universe. Why would we do that? Well, the reason that we use radios to communicate, so radio waves to communicate radio shows, but Wi-Fi and lots of different like television broadcasts, is because it's really good at keeping in information. So it doesn't suffer much like information loss when it's traveling. So if we're going to look really far away to different stars, different planets, different galaxies, the dawn of time, you want a kind of light, a kind of like carrier that will actually keep that information. And so that's radio. The difference with optical, like you say, is that it's not that you can just point a telescope and suddenly you get these images out. You have to do a bit of paint by numbers. So have either of you like done paint by numbers before? You know the kind of thing that I'm talking about, where you've got like, let's say, a picture of a dog and it will be like 1 is brown, 2 is dark brown, 3 is red for the ball or something like that. And when we get radio data in, it's like a paint by numbers. And instead of it just being an obvious picture when you just look at a painting, we've actually got to do that painting. And we say, okay, you know what? A wavelength of 21 centimeters, we're going to say it's red. A wavelength of 25 centimeters, we're going to say it's purple. And bit by bit, we build up our painting until voila, we have a new image of a galaxy that's studying a different kind of element to optical, like it's a different way of seeing things, and you can study different kinds of things.
In the book, at one point, you describe wavelengths in terms of like having your feet in the water and kicking at different sort of frequencies. And one thing that reading your book made me feel is when I look at the ocean, I can see the big, slow waves that are cresting and moving, or I could see the really minute little ones. And that really is a matter of scale of frequency. And that's kind of what you're saying is we're so used to seeing the optical light, which is a certain wavelength, but there are much narrower waves, there are much wider waves, and you can really choose where you're perceiving. We can't look with our eye directly, but as you're saying, the technology translates. But I thought the ocean is a nice way to think about it, that the little ripples are just as fascinating as the big waves or the tsunamis. They're all just telling us different parts of the story of what's happening in the ocean.
Yeah, that's exactly it. And that kind of goes really nice onto how a radio telescope actually works. Because if you've ever seen a radio telescope, it's kind of just these big metal antennas or dishes. And what they measure are these different wavelengths, like different scales on the sky. And it's the mathematics, like in the computational algorithms at the back, like in the computers, which actually adds together all these different, exactly as you described, wavelengths on the sky, adds them all together to create a whole picture. So it's a really good analogy to use the ocean, because if we just use one section, let's say we're just looking with optical light, it's the equivalent of looking at an ocean and just looking at tiny ripples. But you don't learn anything about the bigger scales. You don't see a tsunami coming because you're too busy looking at the ripples. But equivalently, like, you know, you can look at the larger scales and you can miss a lot on the tinier scale. So I try not to get too tribal, even though I've written a book about radio astronomy. I try not to get too tribal about the fact that it's like better or anything than other wavelengths. It's just complementary. It's more, and it's definitely where my heart is, for sure.
So you mentioned earlier this kind of reaction when you're at a party and mentioned radio astronomy or just astronomy in general, that people tend to think of the Big Bang and black holes. And I have to admit, when I started reading your book, I was thinking, oh, another book about the universe. It's going to tell me about the Big Bang and black holes and the stuff that I've just heard a million times. One thing that really stood out with your book is it's so intimate. It's like this very personal guided walk, not through the entire universe, or at least a lot of it isn't. A lot of it is just really walking us through our own solar system. You really get to know each planet through the history of humanity's endeavor to map it, visit it, conquer it in some way. And I just loved every planet. I felt like had its unique personality and story that you're really exposing us. And a lot of the time the story was we realized it's too hard to get there. It's too hard to image it optically. And radio imaging, as you're describing, is kind of the missing key that, we can actually really get to know the planet. So we want to ask you just to share with our reader or our audience here some of the beautiful stories from your book. So for instance, let me just start with the moon, a very familiar thing. I have to admit, I didn't realize this. I'm sure I learned it in grade school and totally forgot. But we always see the same side of the moon, right? It doesn't rotate around relative to our position on the Earth. I thought you beautifully explained how this works. So can you walk us through, why do we just see one fixed side of the moon? Has it always been that way? What happened?
Yeah, sure. So the idea is that you get tidal locking, which is when you have one really massive thing, so in this case the Earth, and one much, much, much tinier thing orbiting it, in this case this moon. And what happens is that when it forms, it might be spinning all over, it might be orbiting like really, really fast, rotating really, really fast. But what happens is that the Earth has such a gravitational pull on the moon that it creates this kind of tiny bulge. Now, this is not something that we would be able to see, but it's this tiny bulge that over millions of years, many more, hundreds of millions of years, billions of years, it will manage to actually pull backwards on this bulge as it starts to kind of start spinning too fast. So you've got the Earth, you've got this moon spinning really, really fast, but it's now developed this little bulge. Now gravity's pulling that little bulge back every time it tries to move forward. And so it acts as a brake. And so over time, over many years, that slows the orbit of the moon down until it's basically in exact synchronization, so that as it rotates, as Earth rotates, as the moon orbits, everything is in sync. And so it's like, I think of two ballet dancers pirouetting. And so they just happen to be pirouetting exactly at the same time, so that every time they turn towards each other and then away, and then towards each other and away. So they never see, one dancer A never sees the back of dancer B. They only ever see the front of dancer B before they turn away. And that's how that works with the moon. And we see it with Mercury as well to some extent. So that's partially in synchronization with the sun as well.
I think one thing that struck me with that story is there's so much chaos in life and in the universe, things that just sort of happen, and often, maybe because of entropy, go from some state of order to disorder. But this is a beautiful instance of the opposite, where we start with chaos and this perfect synchronicity emerges, where the Earth and the moon are just so harmonized, and it's not by chance. It's this actual gravitational force is bringing them into this synchronicity. So I thought it was very poetic.
That's a really interesting insight, actually. I hadn't actually thought of it like that, but yeah, I think you're absolutely right. I think that, and that's why I find so much beauty in the solar system, actually, which I will admit, I was late to the party when it comes to the solar system. I was very much like educated as a cosmologist, like Big Bang, first stars. That's where my kind of research niche is, everything like that. And I was a bit like, planets, they get in the way, move them out the way. And then when I started to really research into the different areas of radio astronomy, about 10 years ago now, really, I started going a little wider. I was just struck by that peace. I'm going to say peace, by the peace in the solar system, and how over so long you can just get this state of being, and we're so lucky. We're so lucky,
There is like a coexistence that the planets have all learned how to work together in a way.
And it has been so violent and so chaotic. You're right. I mean, that's how we think the moon formed, right? Is that a Mars-sized planet collided with Earth? That's not peaceful. But the fact that this incredible moon came out of it, that is just this like real symbol of peace, actually, isn't it? I mean, just look at how it united people for Artemis 2 a couple of months ago. I've not been able to look at the moon the same since, for sure.
Absolutely. Speaking of the moon and astronauts going into space, you have this one particular section in the book where you start the journey of the Apollo mission. And you go into the emotional lives of the astronauts' wives. Do you want to tell us a little bit about that? Because I found that to be absolutely fascinating.
Okay. This was drawn from history, but also, I will have taken poetic license with it. I will not lie. But it was imagining kind of what was it like for the people left back on Earth. that were close to Neil Armstrong and Buzz Aldrin and Mike Collins. Like, what was it like for them? And this also, slightly came because I was watching For All Mankind at the time. And I was like, God, it must have been awful for them, like just having to watch on this tiny screen, like this slightly delayed recording, and like listening in on the radio boxes to find out whether their husbands had survived this unknown mission. And that absolutely fascinated me, that they had to sit there and kind of just chain smoke their way into kind of calming down and live with the paparazzi. And what was it? It was radio waves. It was radio waves that were transporting the voices of their husbands from however far away, across unimaginable distances. It was this radio. And that's like a connection that I really try to underline to people, is that as a radio astronomer, I love using radio waves to study the universe. But I can also never quite get away from the fact that all of space exploration relies on radio communication. Like there's a bit of laser communication that goes on, but if it's cloudy, So whereas radio waves can go straight through clouds, straight through the atmosphere of the Earth, unbothered. That's what makes them such good communication devices. But yeah, I mean, what must it have been like, hey, to just wait? I think that's what made Artemis 2 so interesting this time. Why it captured people. I don't know if you found this, but in the months before, people didn't really know it was happening. Certainly when I was talking to kids, none of them had a clue. And then it happened, sorry, carry on.
Nobody knew until it started blowing up on social media.
Yeah, exactly. And I think why it suddenly blew up was because we had people in space that were basically texting and like images that they had sent, and I have no doubt it went through like a NASA PR office first, but almost instantly uploading it to Instagram and everything like that. And that immediacy of connection I find absolutely fascinating. Whereas if you didn't have radio waves to communicate that, you'd literally be waiting for the hard drive to get back. And 10 days later, downloading the images, and nobody would have cared because it happened 10 days ago.
I thought that was a fascinating point that I have to admit I'd never thought of before, that you really emphasized even with the original moon missions, that there would be such a difference psychologically for humanity to just sort of wait and find out what happens versus having the shared moment. And it did make me think, this is going to sound very superficial, but like Netflix is experimenting more with these kind of live events. And the idea is like, okay, it's great that we have the comfort and convenience. We can stream shows, whatever we want, whenever we want, but we miss that shared experience that I think all of us in this room at least grew up having, of like, oh, there's that certain show you'd watch every Friday night.
Yeah.
We'd all get around and your friends would watch it and you had that bond. And I think Netflix and probably others are trying a bit more of that synchronicity. So I thought that was a great point, that this was humanity's synchronicity moment of finding out what happened. Did the people get back? Did they land? And that the fact that it happened in the live moment, who cares if it's delayed 10 minutes or whatever, it really mattered. It wasn't just something like, oh, we read about a week later that they came back and everything was fine. I thought that was really remarkable to think, this shared experience.
And we were allowed to share every part of it pretty much, like when the toilet broke, we were there being like, oh my God, what are they going to do? Like when the Nutella jar floated past, we were like, oh, I want Nutella. It's just like, I just love it. I love that we were there with them, like for every moment, until they went round the far side. And like, again, I found that fascinating. I found how, certainly in the BBC, like there were real articles about like, okay, they're about to go out of contact. They'll be out of contact for this many minutes. Don't worry, guys. Do not worry. And there was a genuine anxiety about, we can't see them. We can't hear them. They're on their own. And like, because just to be clear, because radio waves can't get through the moon. They can't get all the way through the moon. So that communication was cut off. And communication is a word I'm going to keep coming back to again and again and again, because that is what radio astronomy in particular is really good at doing. In terms of most astronomy, like optical, is all about gathering light that falls upon us. Like we just gather the photons and have a look at what's happening. Whereas certainly in the first half of the book, because it's so close by, radio astronomy in particular has this really like epic ability to use radar. So we're able to actually send radio waves out and bounce it off anything out there and see what comes back. And there's nothing more communicative than that, I think, to kind of have that two-way conversation where you're sending stuff out and you're listening. And yeah.
That also makes me think about future missions, even if we go to Mars and something's blocking the signal. What's going to happen on these future missions, especially when we're thinking about this mathematically, even from the perspective of radio astronomy? Like, how often are we going to end up losing contact on another mission?
That's a really good question. I don't actually know the exact whether like when Mars is going to be eclipsed by other things. I guess there would be moments, yeah. But the main issue with that is going to be the delay. In the delay with the moon is about 1.5 seconds to get there. 1.5 seconds, so it's about 3 seconds delay.
Sure.
Whereas Mars is closer to 4 minutes. In terms of delay, which doesn't sound much, but anyone who has tried to have a conversation with, like, well, anybody like that's just got that little bit of lag in a different country, it's impossible after the lag's half a second, something like that,
Sure.
And this is 4 minutes, so this isn't even the ability to instant message anymore with the family you've left behind. This is now pen pals on email.
This is playing chess by mail.
Yeah, it's, and I think psychologically that's going to be the toughest thing, is that on this 6-month journey, you're going to see Earth get smaller and smaller and smaller and smaller, and that delay is going to get bigger and bigger and bigger and bigger, and then you're not really. Yeah, you become more Martian. It's gonna be very difficult, I think.
You really do a great job in the book, and it's coming through here as well, of capturing the psychological and the emotional side, right? That's science isn't just happening in a vacuum. We can really feel the vastness of the universe, and I think what you're getting at here is the universe is enormous, but as long as you have that link of direct connection to humanity here on Earth, you feel somewhat tethered. But as you're saying, once the astronauts are on the other side of the moon, you feel like now you're in the unknown, you're out there. There's so many, I found very poignant moments of your book where you really felt like it kind of remind you that there are people on all sides of this. And as Autumn nicely asked about the astronauts' wives, here on Earth, there's humans. We're receiving all the science, and the science is happening there. But let's go further back in your story. You have this very touching moment where you describe seeing a comet and crying.
Yeah.
Can you share that with us?
This was a comet in oh Lord, I'm forgetting now. I was about 8 years old, so 1997. So Hale-Bopp. Sorry, it escaped me then. I was thinking it was Halley's Comet for a minute. I was like, I'm not that old. I'm trying to remember when that came around. Anyway, I've just insulted somebody.
Emma, you're dating both of us right now, and that makes Noah seem really ancient.
You don't want to know the comets I've seen.
The one I speak about in the book, the comet I speak about in the book, is Hale-Bopp, which was, I think, 1997, when I was around 9 years old. And I just have this really vivid memory of my dad taking me outside into the garden and to look at this comet, and my mum wrapping me up really warm. And yeah, it just got to be, I don't know how to describe that moment.
But why did it touch you so much? Because it's so easy to look up, to feel jaded. Like even now, sometimes my neighbors get so excited when the Northern Lights are going to be visible where I live. And I'm just sitting in bed thinking, is it worth, I just got the kids to bed. Is it worth getting out at 10 o'clock? There's so many things, or some eclipse. And I see on social media, I have friends or people I know flying halfway around the world. What is so, and I'm asking this slightly as a cynic, what is so appealing and exciting about really experiencing this stuff? I could see 1,000 years ago, but now, like, we have so much going on in our lives, so much at our fingertips. Why does it still have that emotional resonance with you?
I'm sorry. No, I'm gonna challenge you there. It has that emotional resonance because we have everything at our fingertips. It's because it's not on demand. So I've only felt this more as time has gone on. But as a 9-year-old, the internet was just about coming through like publicly at that time. And certainly as a kid, I was much more used to kind of just being able to like go out and see my friends with that kind of immediacy. This was an event which I had no control over. And I remember I was really into Egyptology at the time. I desperately wanted to be an Egyptologist. And I remember learning that the last time that this comet in particular had been seen was in during the time when ancient Egypt, like all of that was happening. And that just made me, I remember it as quite a fearful moment in a way, because I was like, but I don't get the choice over whether I see this again or not. Like, and that as a 9-year-old, that was quite it sounds really bleak, but it was a moment of real mortality actually. And but at the same time, as we all know with bittersweet things like this, there came an enormous like, oh my gosh, I'm looking at it now, and this is incredible. Like, this is an event that I am lucky enough to see right now because it's not cloudy. Isn't that incredible that like something as simple as clouds can be the difference between whether we see these amazing northern lights, or which I would, by the way, kill to see. Like, it's funny, like, and that's no like shade on you. Like, things do become normal the more you see them, but comets, that's very rare to be able to see one that bright. So
It seems like
that's yeah.
it seems like one of the things you're getting at there is this idea of control that we're so used to. I can control what shows I watch and when I watch them. I can control what content I see on the internet on my phone, that we've just grown more in control of our life. And yet when it comes to looking up in space, we have no more control than the ancient Egyptians did, right? We just sit and wait until the event happens. And so it is this kind of awe-inspiring moment, it sounds like you're describing, that to realize I am so insignificant compared to this. I have no control over this. I'm just a passing witness. I could see that kind of spiritual resonance
Yeah,
there.
and it used to give me like, I used to have panic attacks during the early stages of my studying university. It really hit me again actually when I was starting to study cosmology quite in depth. Just like, oh my gosh, we're so tiny both in time and space. And as a human, I've always run towards the things that I don't understand or that scare me a bit to try and understand them. And I think that's the only reason I became a cosmologist, because I was like, I have got to stop being scared of the universe. Like, so I'm going to go study the Big Bang. What a great idea. Yeah, and I think once you it's a real bittersweet thing, I think, when you think about how it's when you're an experimentalist in a lot of physics or any area of science, right? You set up your hypothesis, you set up your experiment, you poke your thing, whatever it is, you poke your atom and you see what happens. Whereas with astronomy, so often we normally just don't get that option. We have to be really smart instead about where we look and when. And where is the most likely place that a supernova is going to go off? Where is the most likely place that we're going to see a very first star? And so mathematically, it all comes down to likelihood, probability, Bayesian analysis, all of this, like, okay, we have to be very smart and work out what's going to happen and when and where.
Now, this also makes me think, because we have so many instances in time where we have no control, like Hail Bob. What does the radio signals of the past look like from all of these other ancient civilizations? How did they look at astronomy and cosmology? And how did some of that play into your research of today?
Yeah, I mean, in every way possible. So you can scratch the surface and you can kind of say, okay, well, the zodiac, comes from like the Chinese astrology, and then you can go further and you can go into kind of the indigenous peoples of Australia, and you can see how one thing that fascinates me there is that they almost see the Milky Way inverted, where for us we describe the Milky Way as like this milky a band of stars across the sky, whereas for some indigenous populations in Australia, then they'll see the dust instead, the black dust lanes between the stars, and they'll see that as a giant emu. And so there's like this, the dust and it's the in-between they see, which I find really fascinating. But yeah, I mean, every way possible as you go back. I think it's interesting how much astronomy has been used to control people. So Christopher Columbus is a famous example because he had an eclipse catalogue. You can predict eclipses really well as soon as you understand like basic Newtonian mechanics and how planets move. You can predict them, and he had a little book of when eclipses were going to happen. And he rode to some island, ran out of food, said, "Well, the gods are going to be angry if you don't give me food. Tomorrow they're going to make the sun disappear." And then it did. And then obviously all of the people would just like have all of the food, have all of the things. So it's not been always used well, but it has always had this aspect of awe for all civilizations, whether it's ancient Egypt and Ra and the sun god, to Chinese astrologers, to Christopher Columbus massively abusing astronomical knowledge.
So Columbus is, of course, a figure we're all familiar with. I didn't know that anecdote, but we generally know Columbus. But there was one character in your book that I'd never heard of that I thought was a fascinating story. I'm hoping you can share with us. Tell us about James Stanley Hay.
Oh, sure. James Stanley Hay was a physics teacher. I like to say that because it's such a fun origin story, and it really reminds people that you can be a scientist and be from so many different backgrounds in so many different careers, and you're still a scientist. So like James Stanley Hay was a physics teacher at a boys' grammar school in Manchester, in the United Kingdom, when the Second World War broke out, and he was drafted into the RAF radar development unit. So didn't even know what radar was, but was enough of a physicist to be taught it for a couple of weeks. And then suddenly he found himself at the head of this big team of people studying the radar defences of the UK, when for one day in 1944, everything went down. Like all of the radar systems, all of our ears listening out for incoming bombers just went dead. They all got jammed. So that's when you get something that's so loud, you can't hear anything else. So what was it? He didn't really have a clue, but he worked out from all of these different antennas in the United Kingdom that roughly when the sun was up over these 2 days, that's when like the network was really, really being jammed. And so he thought, okay, well, maybe it's something astronomical. I can't tell the moon from Jupiter. So he rang the Royal Observatory here. And they said, well, there is a giant sunspot on the sun right now, but didn't you know the sun can't create radio waves? Nothing can create radio waves outside the Earth. But he didn't have that bias because he was a physics teacher, because he wasn't an astronomer. And so he just put together the evidence and realized that, it was the sun. It was this massive sunspot that was going across the sun that had thrown out a huge amount of particles, atoms, and that collided with Earth's atmosphere, created all of this radio wave noise, basically, that had overwhelmed the entire defense network of the United Kingdom. And we were just damn lucky that nobody invaded on those 2 days, because we wouldn't have had any notice. And it just shows you we have only become more dependent on technology, on anything that uses radio waves, Wi-Fi, nuclear submarines, using this kind of GPS that uses radio signals. And we still have a sun which can throw tantrums whenever it likes. We do not have control. And so we're only more subject to massive problems when it comes to space weather. And radio astronomy is one of the ways which we're hoping to be able to one day mitigate that, if we can get good enough at predicting when the sun is going to chuck something out that's a problem.
So since you brought up jamming radars, I can't resist, and we have a math audience, just taking a minute to share an interesting thing I just learned not too long ago. So you know that warfare today is being taken over by drones, right? Everything is about drone forces and all this. And drones have to communicate with each other, with the base. So they're using radio signals. And naturally, a defense you might want to have against a swarm of drones is to jam their communications. So the defense against that kind of attack is they communicate on lots of different frequencies. So you'd like a jammer that operates on many different radio frequencies simultaneously. And it turns out that there's an inventor that's offering a product that seems to be effective at this. And the idea, the reason I love this is it's so mathy, is it's a fractal antenna. So it's an antenna that's shaped almost like a Sierpinski gasket kind of thing, where it just keeps bending and subdividing in many different iterations of the larger scale. So it actually covers a wide spectrum of frequencies by kind of using fractal geometry. And this apparently is useful even in our cell phones, because our phones have to connect to lots of different towers and communicate on different frequencies. And you don't want a phone that has like 20 different antennas. You want one antenna. But if it's a fractal antenna, it's tantamount to having many. So I just thought this is amazing that fractals are like powering our cell phones and maybe like playing a role in drone defense. But there's another story about radio jamming.
No, that's super useful, because one thing I wanted to get across was that when we think about an optical telescope, it's very easy to imagine it's Galileo with a tube, right? But when you say radio telescope, I realize I've not really described what that can look like a lot of the time. And that's because it can look like so many different things. It can look like an antenna that you might have pulled out on the bonnet of your car or on your Roberts radio, or it can look like a satellite dish on the side of your house. And the ones that I use in Western Australia are exactly what you're describing, which are what we call Christmas tree antennas, where they get ever larger in bigger scales of the same shape. And the reason we can do that is because or the reason we want to do that rather, is because we can gather radio waves of so many different wavelengths that they're studying completely different things all at the same time. So whereas with Hubble or something like that, you're looking and you're kind of, okay, I am looking at a galaxy now. I'm looking at a few galaxies. Lovely. Love it. Go Hubble. But with the SKA, the Square Kilometre Array, you switch it on. You've got 130,000 of these antennas eventually all linked up to make what is a pretend but actually working massive radio telescope. And not only is it gathering the wavelength which is telling you whether there's alien life, whether there are alien signals coming from this thing, it's also looking at spinning stars, pulsars, creating like a cosmic GPS system. It's also looking at the dawn of time. It's looking at the cosmic dawn, the era of the first stars, all at the same time, because it's got this incredible geometry. And such a nerd for radio telescopes now. Like, I was so underwhelmed by them at first. And I was like, I want clean rooms. I want NASA security clearance. And then radio telescopes, honestly, just look it up. Google where you are. There will be one, like, within a decent drive of somewhere where you are or somewhere you're going on holiday. And you can just walk up to these things like nobody cares. You just drive up and you have a good look around, and you just get that moment of, well, I get that moment of peace anyway, knowing that this piece of machinery that looks kind of exactly like it did in the 1950s, and sometimes it is exactly what it was in the 1950s. But because it's got all of this mathematical, like, algorithms and software that's all been updated on the back, it's able to do just astonishing things, like take images of black holes. And like, yeah, I cannot get enough of it.
Well, let me just highlight here. So you heard it first, Breaking Math audience. If we ever hear from alien life, it may be in large part because of the geometry of fractals. I think that's what Emma just said.
Yeah, sure, why not?
And Christmas trees. They can.
I mean, okay, you're talking to the wrong person, because I'm gonna just hijack this podcast and just talk to you about aliens right now, because like it is all about maths. It is all about maths, because how do you communicate with an extraterrestrial intelligence on another planet? Firstly, why are we looking in radio? Because radio can get through atmospheres. The physics is the same whether you live here or near Alpha Centauri, so they're going to be using radio. But how do you know you're listening to aliens? Well, you need to be able to send a signal which will definitely be known. And you can't use English or French. What you use is mathematics. You send them the digits of pi in binary, or you send them, for example, what we have done in the 1970s was we sent an image and it really looked like Space Invaders style, pixelated, like a little person and some DNA. But how do you tell them that, like, the flashes of radio light that you're sending, like almost like a Morse code in binary, how do you tell them that's actually an image and you need to make it into this 2D image? You make it so that you send exactly a semi-prime so that they go, hey, that's weird, it's a semi-prime, it's a product of two prime numbers. I wonder if those two prime numbers are dimensions. And so you send them a semi-prime and they're like, oh, okay. And you play with it, and that's how you signal to people how to create these different dimensions in images. So yeah, it's all maths. That's the language, right? It's the language of the universe.
Now, something that we haven't touched on in this at all is, how do you think, or already has AI even become part of this picture with radio astronomy, with telescopes, with all of this new technology? Are you using that in your research at all?
Yes, and this is where I have to try not to get defensive. We've been using it for like the best part of a decade, if not longer. And the reason for that is because when you're creating these algorithms in machine learning and artificial intelligence, you need to train them on really big data sets to get them to work.
Of course.
Now, before we had the huge computational power to kind of create data sets or scrape the internet for data sets, they had to go looking for data sets somewhere else. And who's got the largest data sets? Oh, wait, that's us. Because we've been downloading the universe now for quite some time. And there's a lot of data. So, for example, very early on in this kind of development of the AI field, it was used as a galaxy classification tool. So we had so many tens of thousands, hundreds of thousands of images of galaxies, and we needed to just basically say spiral, elliptical, spiral, elliptical. So that was one of the very earliest things. It was just image recognition, same as blueberry muffin or pug dog, right? Like, it's just that. Whereas now, yeah, absolutely, now that it's being developed outside of astronomy, a huge amount then we're taking from that as well, and especially with radio astronomy, when it comes to the level of data that's coming into our telescopes, it's exobytes, and we are basically blowing up our hardware and melting cables because of this data rate. And so we need to delete on the fly. And you have to decide very quickly what is good data and what we need to delete. And for that, it's like these tiny stock exchanges in microseconds. You need something that can very quickly evaluate whether it's a buy or sell. And so that's the kind of AI that we use is to say, right, no, chuck that data, keep that data, chuck that data. And the heartbreak is, of course, that it might chuck something which has first contact or something like that. But we just have to trust the maths, and we have to trust. I keep saying maths. Sorry, I can't make myself say math. I keep trying to make myself
It doesn't matter. It doesn't matter to us.
But Emma, now I have this idea for a sci-fi story floating in my head that these aliens are going to try to contact us, and the AI is going to be like trying to hide the fact that they exist, and it'll purposely delete their data so the AI can be our own super intelligent being instead of the aliens.
Oh, we need to write this.
There you go.
So now I'm curious, what will we see in future technology for radio astronomy or in the field?
I think it's going to be this continuation of a mix of the old technology that we're used to seeing, like the literal pieces of metal bolted together and antennas, but with an increased like computational mathematical background, and then on the moon, probably. So I think that what we're going to see is kind of almost very much what we've seen on Earth. Let's say if you've ever seen it or Googled it, Arecibo in Puerto Rico was this incredible radio telescope, which about 300-meter diameter dish. It was unbelievable. If you ever, I went and your eyes just kept focusing in and out in the scale because they couldn't quite understand what it was looking at. And there's so many ideas of, for example, putting one of those on the moon, but like in a crater And there's some even ideas of actually using the crater on the moon actually kind of as a reflective dish surface, which I just love. Like, and this is the ingenuity I love in radio astronomy, is that, like, because we're not bothered with the whole clean room, let's make everything all pretty. It's just like, right, boots in the dust, people, or boots in the regolith. Let's let's work this out. And the idea actually would be to, where we kind of started this podcast, is to where we're going to end up is on the far side of the moon, because Earth is only getting noisier. It's incredibly noisy in terms of radio. We do a darn good job of filtering it all out with all of these algorithms, but actually if you go on the far side of the moon, then all of those Earth signals can't get through the moon, just as the Artemis 2 signals couldn't get through. And so it blocks. It's a shield. And so if you're on the far side of the moon, suddenly it's quiet in the radio. And that means that we can look or listen or gather that radio light from so much further. And it will allow us to go right back to the cosmic dawn and start understanding about the very first stars and the very first baby black holes. Glorious things like that.
Just to kind of wrap up, what's one thing you'd like to tell people when they look up at the night sky? Just something to have in mind as sort of summarizing takeaway from our conversation.
I could pick so many things, but I'm going to ask people to consider the space between the stars. If they're going out and they're looking at the night sky, it's glorious to look at the moon. It's glorious to look at the stars. But I want you to just take a moment and look in between and consider the fact that if we had a switch and we could switch off the optical and turn on the radio in your eyes, then you would see something completely different. You would see the galaxy splashed across the sky. You'd be able to see kind of like the remnants of stellar explosions. And you'd be able to see the universe in a completely different way. And that's what I want to leave people with, is that the radio astronomy is nothing terrifying. It's you just take one more step with me. Come on, guys, one more step, and you get to see the universe in a completely new light.
And that was Dr. Emma Chapman on radio astronomy, invisible light, and what it means to listen to the universe. What I love about this conversation is that it reminds us that science is not only about what we can see. Sometimes it's the important information that's hidden in the space between things. That can be stars, wavelengths, a signal sent, and a signal received. Radio astronomy gives us a way to translate the hidden universe into something we can understand. So until next time, when you look up at the night sky, just don't look for stars. Think about the invisible radio light passing through you, from Wi-Fi, distant galaxies, and even the beginning of the universe itself. So until next time, stay curious and stay informed of the world around you.